Perhaps you're at the end of an introductory organic chemistry class and you've learned all this enolate chemistry and so on, and you're wondering what you can do with it as a life science major. It's my job as an organic chemistry professor to relate the chemistry that you've processed into something very significant, like the Krebs cycle. What I'm going to suggest to you here is you can use chemistry to remember Krebs. Learning the Krebs cycle is like putting the skin back on an onion, layer by layer, as you build knowledge. At the core, it's just learning the names of the intermediates. I gave you a silly mnemonic for doing this. I don't really want to say it again, but it helps you be able to name the intermediates in the cycle. And that's a good start. The next step, I think, is chemistry. How is each intermediate transformed into the next one? Now, we don't need to know exactly the mechanism. That's not important at this stage. What we're interested in is a parallel organic reaction that would occur on each of these substrates to get us where we need to go. Of course, enzymes, they don't do it that way. They just don't. They put things in an active site and they pull on groups here and they push on groups there. They pull off protons and they add electrophiles, for instance. It gets complicated to understand that. But to understand that, you must understand the organic chemistry that's going on that converts one intermediate to another. Okay, officer, can I keep selling sex for money? I got bored, you see. I started with officer this time because we are going to begin with oxaloacetic acid. The first step involves acetyl-CoA. Acetyl-CoA is a big molecule. I've said this before. Forget most of it. I've said that before too. All you really need to worry about is the acetate group on the end, because this acetyl-CoA is an enol or an enolate equivalent. We have to react acetyl-CoA with oxaloacetic acid. Good news. The ketone alpha to the acid in oxaloacetic acid is activated because of the electron withdrawing group, the carboxylic acid that's on it. We have a choice. How do we represent acetyl-CoA? As an enol or an enolate? So let me choose, almost arbitrarily, enolate. We form an enolate from acetyl-CoA. That enolate adds to the ketone of oxaloacetic acid. We form a tetrahedral intermediate, a negative charge on the oxygen by pushing the arrows. And then in the next step, that O- is protonated. We've added 2 carbons to oxaloacetic acid. Think in terms of what we're doing. We're taking in food, we're converting it to acetyl-CoA, and that acetyl-CoA has to be burned. And as we burn it, let's pick up a little bit of energy to use later on. Now, the first transformation also requires a hydrolysis. We have a CoA ester here. We don't need it to go to citric acid, the first intermediate in the Krebs cycle. Let's hydrolyze. Let's choose randomly again, OH-, add to the carbonyl of the thioester, tetrahedral intermediate. The electrons bounce back and eliminate S-CoA. A simple hydrolysis reaction takes us where we need to go, citrate. Stop number 1. The next transformation is citrate into isocitrate. As the name implies, it's an isomerism, same molecular formula. What do we need to do to transform that molecule into isocitrate, take off water, and add another water in a different orientation? Of course, you can do that chemically in a synthetic lab by protonating OH and losing a proton and water dehydration reaction. And then you could hydrate by acidic conditions, adding water. But an enzyme is so much more sophisticated than that. It will do it gently at physiological temperatures under physiological pHs. Enzymes can do it under neutral pH. Let's represent that here as then a dehydration and a rehydration and say no more about it. Isocitrate then, we've arrived at the second stop. The next one looks a bit more scary. We've got to take isocitrate to alpha ketoglutarate. And you'll note in this transformation, we give out CO2. But think again what we're doing. We're taking in food, we're consuming it in the Krebs cycle, we're giving out a little bit of energy, I haven't told you how yet, and we breathe out CO2. That CO2 is coming from the acetyl-CoA, which comes from fats, which comes from carbohydrate. There are two steps to this next transformation in the cycle. And the first one is an oxidation. And for that, I need to remind you about NAD+. Remind you because I've already talked about that in my last video. NAD+ is a master of hydride abstraction. It oxidizes polar group, particularly alcohols to ketone. And the hydride we can represent as H-. That's almost a joke under physiological conditions. You can't have H-, but it's symbolic of the hydride that's removed. Alpha to the OH in the alcohol, alpha to the OH in isocitrate to give alpha ketoglutarate eventually by loss of a proton forming that double bond. NAD is therefore converted to NADH. But we're not at the next station yet. Let me draw the molecule in a different way. I want to blow up that acid, feed in the electrons from the O- of the acid, push the arrow, break a bond, form an enolate with an O- charge. The electrons flow from one O- to another, but in doing so, give out CO2, entropically favored. That is a decarboxylation. It's a decarboxylation typical of decarboxylating 1,3 keto acids. 1,3 keto acids are actually quite unstable. They undergo loss of CO2 and enolate formation very easily. That takes us to another station. We have arrived at alpha ketoglutarate. Our next transformation is turning alpha ketoglutarate into succinyl-CoA. It's a bit of a messy one. We don't talk about this in polite company because there is no simple chemical parallel. I don't think you're quite old enough to learn about this yet. Maybe at the end of the video, we'll talk about this one. Keep studying sector. Now we've got to change that into succinate. Easy. It's just a hydrolysis to get rid of the S-CoA now. Let's represent that with a base, tetrahedral intermediate, negative charge, push the electrons back in, S-CoA leaves again. We've done our hydrolysis. We're at 6 o'clock in the Krebs cycle. We've formed succinate. The next step is to oxidize succinate to fumarate. To do that, we have to take 2 hydrogen atoms away, dehydrogenase. The oxidizing agent that nature uses to remove 2 hydrogen atoms in an apolar reaction is flavin adenine diphosphate, as I've talked about before, otherwise known as FAD. FAD is going to go to FADH2. Remember, it's the flavin end of this reagent which captures the 2 hydrogens. It adds them across the heterocycle and it forms FADH2. And therefore, fumarate is formed. We're at the next station. The next step is to convert fumarate to malate. Look at what we're doing here. We're simply adding HOH. We are hydrating the double bond. We can show that chemically as the water adding. In an enzyme, it's bound to involve a proton near the alkene and a water being encouraged to add from the other side. And in fact, the enzyme does this stereospecifically to give one enantiomer. But at the end of the day, it is still just addition of water across a double bond. This is the penultimate intermediate. One more stop to go. Conversion of malate to alpha-ketoglutarate. We know all about this. It's an oxidation of an alcohol. It's going to be via NAD+ to abstract hydride to give us the ketone. We have arrived at the final stop, oxaloacetic acid. And we've arrived at the first stop again. We've completed a cycle. So what is this mysterious reaction, alpha-ketoglutarate to succinyl-CoA? It's messy because we can't draw just a simple process for losing CO2 from a ketone and replacing it with S-CoA. It just doesn't work. For this, we need reinforcements. And the reinforcement that we call in is thiamine diphosphate. Thiamine diphosphate is a cofactor. It's going to get involved in the action and then disappear. Thiamine diphosphate is a thiazolium. It's cationic. And that makes the CH between the nitrogen and the sulfur a little bit basic. A base in an enzyme then can deprotonate that CH and it forms a zwitterion. That zwitterion, actually in chemistry, you might represent as a carbene. But I like the zwitterion representation much better, especially for a mechanism like this. That zwitterion is still nucleophilic on the carbon that now bears a negative charge, even though the overall molecule is neutral. Attack! Attack! That zwitterion attacks the ketone group of alpha-ketoglutarate. We form a tetrahedral intermediate. It gets protonated, same old story that we've learned so many times. The electrons can feed back from the oxygen and then back onto the N+. I've turned that side of the molecule upside down to put the N+ on the top in this diagram. Note what the N+ did. It stabilized the negative charge of the thiazolium, and then it donated electrons from the C-, and now it's accepting them back. Push-pull type process. Push the electrons down from the O-, form CO2, entropically very good, break the bond between that CO2 unit and the rest of the molecule, and push towards the positive charge of the thiazolium. Formation of a double bond nitrogen is like formation of a double bond O- in decarboxylation of alpha-keto acid. The same process we've already seen. So then we have a nitrogen on a double bond. It looks like an enamide. It is, and it's further activated by the sulfur. That's nucleophilic on the beta position. It adds to an electrophile. What's the electrophile? Well, in cells, there's an equilibrium of cyclic disulfide. Let's not worry too much about what that disulfide is. Push again from the heterocycle, push-pull, and add to the beta carbon, puts the sulfur there, opens the 5-membered ring. Let me draw that in a different way and set it up for the next transformation. We've got a tetrahedral intermediate. Let's push the electrons down and say goodbye to the heterocycle. Say goodbye to the thiamine component. It's a cofactor. It goes around and around in a catalytic cycle. We only need a catalytic amount. It's the sidekick for the enzyme that's doing all this chemistry, but an important one. But we're still not at the next station yet. We're still at a thioacid, that's good, but it's not a thioacid of CoAs. Thioacids exchange readily with S- groups, or thiols. Attack with CoAs on the carbonyl, tetrahedral intermediate, O-, O- comes back, elimination of one of these two in equilibrium. Let's push out the disulfide that we took up from the 5-membered ring and leave a self with a thioester of S-CoA. We have arrived at succinyl-CoA. That's the hardest step in the process. I hope you followed it. I think many of you might think you followed it, but be unable to draw it when you try again. Try again. It's okay to get things wrong. Look at how it really works. Try again later, and eventually you will get this one. I think it's my job as an organic chemistry professor to relate the chemistry that we learn, which can sometimes seem dry and irrelevant to life science majors, to real processes. And the Krebs cycle gives a fabulous opportunity to do that. Thanks for being here. I love teaching you via these videos. I hope it helped. Bye-bye.
Sun is shining bright. Pack your bags, let's go. Feel the summer light. Chasing dreams, you know. Waves are calling now. Sand beneath our feet. Find the way somehow. Heartbeats in the heat. Oh, we're flying high underneath the sky. Summer nights and days in so many ways. Open roads ahead, wind in our hair, colors turning red, no more need to care. Oh, we're flying high underneath the sky. Summer nights and days in so many ways. Waves are calling now, sand beneath our feet. Find the way somehow, heartbeats in the heat. Oh, we're flying high underneath the sky. Summer nights and days in so many ways. Laughing till we fall, dancing through it all. Magic never fades with each step we made. Oh, we're flying high underneath the sky. Summer nights and days in so many ways. Oh, we're flying high underneath the sky. Summer nights and days in so many ways. Laughing till we fall, dancing through it all. Magic never fades with each step we made.